So you have just seen that we can diagonalize a matrix as long as it has an eigenbasis, meaning that it has n linearly independent eigenvectors, where n is the size of the matrix. Yeah? And when this happens, you change the basis to the eigenbasis, and the resulting matrix is diagonal always. So let's formalize all this and write some formal definitions. So now I am using golden boxes, okay? These are formal definitions. So a matrix is said to be diagonalizable if you can find a similar matrix, and remember that similar matrix is simply the name given to the same linear transformation but written in another basis. Yeah? A similar matrix that is diagonal. So if you can change the basis of a matrix using the similar matrix equation, which is, sorry, not m minus 1, m prime equal inverse of a times m times a. If you can find m prime that is diagonal, m prime is a similar matrix to m. If m prime is diagonal, then m is said to be diagonalizable. Okay? What's the condition for a matrix to be diagonalizable? So this is the formal condition. A matrix, or let me write the size, an n times n matrix, so n rows and n columns, is diagonalizable if and only if it has n linearly independent eigenvectors. In other words, an eigenbasis. Okay? And this makes sense because if a matrix has n linearly independent eigenvectors, it means that the n vectors span an n-dimensional space, which is the space that this matrix is operating on. And therefore, you can use those vectors as a basis, called an eigenbasis. And when you use the eigenbasis, as you know, as I proved to you in the last video, the resulting matrix, when you change the basis to the eigenbasis, is always diagonal. Okay? So the recipe for diagonalizing a matrix, so we are going to write the same thing, the same recipe that we know, but to the m prime, instead of calling it m prime, since we know that m prime is now going to be diagonal, we are going to call it D, the diagonal matrix, okay? So then M or D, the diagonal matrix, is equal to A minus 1 times M times A. Or you can write it in the other way around, M is equal to A times D to the, times D times inverse of A, okay? So matrix M is diagonalizable if you can write it as a change of basis matrix times a diagonal matrix times the inverse of the change of basis matrix, okay? Which, if I write this explicitly, let me write it fast. So matrix A is the change of basis matrix, and therefore it has the eigenvectors written as the columns. Right? That is the change of basis matrix. Then the matrix D has the eigenvalues in the main diagonal. So it has lambda 1, lambda 2, all the way up to lambda n. And it has zeros everywhere else. And then the inverse of A is simply matrix A but inverse. So let me copy matrix A, but we do the inverse of that. Okay? So this is a very simple recipe, because notice something. You have a matrix M, whatever that matrix is. You find the eigenvectors v1, v2 up to vn, and the eigenvalues lambda 1, lambda 2 up to lambda n. And then automatically you know that you can do this. The matrix with the eigenvectors multiplied by a diagonal matrix that has the eigenvalues multiplied by the inverse of the matrix with the eigenvectors is equal to M. So you have kind of split M into 3, and the center one is a diagonal matrix. Okay, this is called diagonalization of a matrix M. If you want to write the usual basis, the usual Venn diagrams of vector spaces, so we have the input space and the output space in the old basis, x hat, y hat, and matrix M. And then we have the basis of the eigenvectors. So this is the basis with v1 and v2. And we still have the same linear operation. So it corresponds to the same operation as M, but in the new basis. And this new operation is a diagonal matrix. And the elements of the main diagonal are the eigenvalues. Okay? And then here we have the matrix A and inverse of A, which are just the change of basis matrices. Okay? So this is called diagonalization of a matrix. And the summary of everything is in this recipe and in the definitions above. Okay? Thank you very much for watching. Let's see next we will see some applications of diagonalization.